Hi there. So this one's nuclear physics, it's A level, and it's the energy mass relation. So Einstein, or as you correctly pronounce it, Einstein, because obviously it's German, did this work in 1905. So what he actually showed is that the mass of an object increases, or indeed decreases, when it gains or loses energy, which might sound a bit strange, but literally everything. So when there's conversions of energy, there's always changes in mass. What we'll do is some calculations in a minute to see how much the mass changes of everyday objects that undergo energy transfers. So the equation is really famous. E equals mc squared. A lot of people think that this is what Einstein got his Nobel Prize for, but it wasn't. Although, to be honest, this is probably Nobel Prize worthy. He actually got his Nobel Prize for the photoelectric effect. So m is the change of the object's mass, and c is the speed of light in a vacuum. So 3 times 10 to the 8 meters per second. And obviously c squared, that'd be 9 times 10 to the power of 16. Right, so you might want to make some notes, write that equation down. So if you want to have a go at this one, you want the change in mass. Right, so if you've attempted that, let's have a look at it. So we're going to use E equals mc squared. And we want the change in mass, so we need to get the energy first of all. So we've got 10 watts for 10 hours. So nice and easy for A-level students, so should be energy is power times time. So we've got 10 watts times, so we've got 10 hours, and then it's 60 minutes, 60 seconds, so 3,600 seconds in an hour. So that gives an energy of 360 kilojoules, 360,000. And then change in mass is going to be energy divided by c squared. So you've got your 360,000 divided by 3 times 10 to the 8 squared, which is 9 times 10 to the 16. So that gives us a change in mass. I'll write it like that. 4 times 10 to the minus 12 kilograms, which is obviously just outrageously undetectable. But still, that energy transfer will elicit a change in mass. But it's immeasurable, so it's of no importance. Let's have a look at another example. Right, so if you want to pause and have a go at this one. Right, so we've got a 2,000 kilogram car, accelerates from rest to 40 meters per second. So we're going to use equals mc squared. So mass is energy divided by speed of light squared, so we need the energy. So obviously this is a car that's moving, so we can just use kinetic energy, half mv squared. So half of 2,000 is 1,000 times 40 squared. So that's 1.6 times 10 to the 6 joules. And then to get the change in mass, we need to do the energy transfer divided by c squared. So we're going to divide that by 9 times 10 to the 16. So that gives a change in mass of 1.8 times 10 to the minus 11 kilograms, which again is obviously completely undetectable. But apparently, that's what happens. So what I want to do next is there's 4 exam questions. So where this does, become detectable and make a big difference is when you're dealing with really small stuff. So nuclear reactors, obviously, use uranium-235 or plutonium-239 as fuel. And when they undergo fission, there is large changes in masses that release a lot of energy, which is obviously where nuclear energy comes from. So let's have a look at this. If you want, you can have a go at this one if you want, and I'll take you through it. If you've struggled with this one, a lot of people do. I always get asked by students about questions like this all the time. but they're relatively quite straightforward. So what rate at which energy is transferred, so that's obviously power. So what we need to do first of all is calculate the energy. So we're going to use E equals mc squared. So we've got 4 times 10 to the minus 6 kilograms per hour multiplied by speed of light squared, which is 9 times 10 to the 16. So that gives us 3.6 times 10 to the power of 11 joules. And that's joules per hour, because obviously the mass, the mass difference that's given is per hour. So rather than hours, we need to do seconds, because that's what power is, energy transferred per second. So the way to do that is just to divide by the number of seconds in an hour, which is 60 times 60, 3,600 seconds. So if you put that in your calculator, that'll give you the rate at which energy is transferred due to nuclear fission. And that gives you 100 megawatts, or 1 times 10 to the power of 8 watts. So that's B. Right, we'll do a couple more of these for some more practice. So as you can see, it's basically a recycled question with different numbers. So this should be really straightforward for you. So this time we've got 6 times 10 to the minus 6 kilograms per hour. And again, we want power output. So total energy equals mc squared. So the mass change per hour or decrease this time is 6 times 10 to the minus 6 kilograms multiplied by 9 to the power 16 for your c squared. So if you calculate that, that will give you 5.4 times 10 to the 11 joules. And that's obviously joules per hour, same as last time. It's given in kilograms per hour, so that's joules per hour. And then we need to divide by the number of seconds in an hour. If you're wondering why that is, obviously per hour is divided by an hour. So if we change that into seconds by putting in the number of seconds in an hour, 3,600, as you can see, that gives us joules per second, which is watts. All right, so if you calculate that, so I'm just going to divide that by 3,600. That gives us 150 megawatts. Ignore that M, that's rubbish. But yeah, B. If you got that well done, let's do another one. There's 2 more. The final one's a little bit different. Right, and as you can see, basically the same question again, different mass decrease. So if you get this wrong, well, I don't know what to say, but you definitely shouldn't be getting it wrong. So 9 times 10 to the minus 6 multiplied by 9 times 10 to the 16. Watch me get it wrong now. I put it in my calculator wrong. So 9 times 10 to the minus 6. So 8.1 times 10 to the 11. And what you might notice here is this one. Distractor answer. Yeah, don't fall for that. So that's, I'm on about getting it wrong. I've just written watts like an idiot. That's joules per hour. So we need to divide by 3,600. So if you do that, you'll get 2.25 times 10 to 8 watts, which will obviously round up to answer A. Right, there's one more. I think this one's slightly different. Yep, definitely a bit different. And I'm going to have to explain this as well. Probably, unless you already know it, then you can just use it as practice. So it says, during a single fission event of uranium-235 in a nuclear reactor, the total mass lost is 0.23 U. Use atomic mass unit. That's on the data sheet. If you want to check it, I believe, no, I should know this. It's 1.661, I don't know why I've written 11. 1.661, it's times 10 to the minus 27 kilograms. So what you can do with that is obviously convert that, just multiply them together, and it'll give you the mass. So be careful with that one. That's on data sheet. So atomic mass unit it's called. There's also an energy on there if you've had a look at it, on your data sheet. We'll look at that next when we do binding energy and binding energy per nucleon. Anyway, back to this. So let's deal with that mass first. So if we multiply them together, so 0.23 times the atomic mass unit, we'll get a total mass decrease per fission event of 3.8203. I'll just use full number, times 10 to minus 28 kilograms. There is another way of doing this, but this way is completely fine as well. Right, so the other thing, if you want to finish that, you can pause it. Right, the other thing we've got to deal with is this. So it's 25% efficient. You're going to be careful. So it says required to generate. So if you do your efficiency equation, so efficiency is useful energy transfer divided by total energy input. So our efficiency is 25%, so 0.25. The useful is the required to generate, that is the useful power. So that's going to be 900 megawatts. So to get the total input, and remember that energy is coming from the fission events. So you need to do 900 divided by 0.25, a quarter. So times that by 4. So the total energy from the fission will be 3,600 megawatts. So there's an extra step there. Right, so what we need to do is look at that mass that we calculated and figure out the energy transfer from a single fission event. So we need to do equals mc squared. So we've got the change in mass, 3.8203 times 10 to minus 28. And then multiply that by speed of light squared. Sorry, my handwriting's terrible. So that gives us an energy transfer for each fission event, which is 3.4, let's do 3.8, times 10 to minus 11 joules. So obviously that's joules and that's power, but megawatts is megajoules per second. So we can just use both these numbers because that's joules anyway, because we're working per second. So if we divide those, so do the 3,600 megawatts. So 3,600 times 10 to the power of 6 divided by, so that's total power, and we've got or total energy per second, and then divide by the energy per fission event. That gives us answer C. All right, if you got that, well done. And next we'll be doing binding energy and binding energy per nucleon. All right, thanks for that. Cheers.